Now that we've introduced the integral and we do have the integral test, but more importantly the limit comparison and the comparison tests, let's do a few exercises from the book. We are asked to establish the convergence or divergence of this series. And you can do whatever you want. But since this is taken from the comparison and limit comparison test, why don't we practice that? What are you going to do? Well, again, the idea is that this negative one is negligible. So you can do a limit comparison with the series 1 over root n. And what do you know about this series? This is a divergent p series where p is 1/2, which is less than or equal to 1. So if we do the limit of one divided by the other, or the limit of root n over root n minus 1, you see easily that we can factor out a root n from the denominator. The root n's cancel, and as n goes to infinity, this goes to 0, leaving you with a limit of 1. Again, 1 is bigger than 0 and less than infinity, so both series converge, or both series diverge, but we started out with a divergent series. So the series 1 over root of n minus 1 diverges as well by the limit comparison test. Just for fun, shall we redo this question with the comparison test, where we have to establish an inequality? Let's do it. Using the comparison test, negative 1 is less than or equal to 0. So square root of n minus 1 is less than or equal to square root of n. And if we multiply the whole thing by 1 over root n minus 1, which is a positive term, the inequality remains. Right, again, this is equivalent, as you know, to cross multiplication. So if you're more comfortable with that, please go ahead and do that. And what do we get? We get 1 over root n less than or equal to 1 over root of n minus 1. But now, square root of 1 over root n is a divergent p series, as we noted before. So the smaller series diverges, so the bigger one diverges as well. By the comparison test. Needless to say, you're not going to get two tests contradicting each other. right? Either both tests will agree, or it is possible that one test does not apply. Or, if you had a limit of 0, then this comparison test would not have told you anything. The limit comparison, I mean. So there it is. Consider this. We're again going to use a limit comparison test here. The idea being, if you look at the denominator, the dominant term is n cubed. This plus 1 here is really meaningless for large values of n. Similarly, in the numerator, the dominant term is n. You can neglect the minus 1. So this essentially looks like an n over n cubed for large values of n. So we're going to do a limit comparison with the series n over n cubed or 1 over n squared. What do you know about this series? This is a convergent P series where P is equal to 2, which is bigger than 1. Let's apply the limit comparison test, see what happens. So 1 divided by the other. You divide by a fraction, we're going to multiply by the reciprocal. So that is n squared, n minus 1 over n cubed plus 1. Let's factor out, you have options. Again, you can do L'Hopital's rule, or you can factor out, let's factor out an n from here and an n cubed from the denominator. So that gives us n cubed times 1 minus 1 over n cubed times 1 plus 1 over n. The n cubes cancel out nicely. As n goes to infinity, 1 over n goes to 0, 1 over n goes to 0, so you get a limit of 1. Coincidentally, we've been getting limits of 1 all the time. That is purely coincidental. That doesn't have to happen. As long as you get a limit between 0 and infinity, that's what's important. So 1 is between 0 and infinity. So both series converge or both series diverge, but this one converged. So your series converges. So the series n minus 1 over n cubed plus 1 converges. I'll invite you to redo or to consider this series using the comparison test. You'll see it's a little tricky. You have to establish an inequality. And there's a little bit of work to do there. But you're certainly encouraged to try it. Consider this. This is an example now where you don't have much of a choice. You have to use the comparison test. Why is that true? Imagine taking a limit of this thing. A limit of one function over another. I mean, you know, maybe you're thinking to yourself, numerator kind of behaves like a k. Denominator kind of behaves like a k cubed. So I'm going to do a limit comparison with 1 over k squared, or k over k cubed. But the sign squared never disappears. And as k goes to infinity, that thing does not have a limit. So we're going to want to stay away from limits for this kind of example. Luckily for us though, you know that sign is between -1 and 1. So sine squared, which is something squared, so you know it's bigger than or equal to 0, is at most 1 as well. And if you multiply this whole inequality by k over 1 plus k cubed, you see that k sine squared over 1 plus k cubed is less than k over 1 plus k cubed. So if we can establish the convergence of this series, we're good to go. If the larger series converges, then the smaller series will converge as well. So can we establish convergence of this? Let us consider the series k over 1 plus k cubed. Here, the denominator, that 1 here, is negligible. The denominator kind of looks like k cubed, right? The dominant term is k cubed. So we're going to do a limit comparison with the series 1 over k squared, which is a convergent p-series. And if you do a limit comparison, 1 divided by the other, this is easily seen to be k cubed over 1 plus k cubed, which has the form infinity over infinity if you do a L'Hopital's rule. Once again, we get a limit of 1. 1 is between 0 and infinity, so both series converge, or both series diverge, so this series converges by the limit comparison test. And since this series converges, then the smaller series converges by comparison. So this converges by the comparison test.